Let's welcome Sukbin for his exciting talk.
Down perception, I feel like. All right. So it's my great pleasure to be here, and I'd like to thank the organizer, volunteer, and the staff for putting this great event together. And before I get started, some of you may not know NIU Shanghai. So NIU Shanghai is one of the portal campuses of the NIU. So we are in New York and also Abu Dhabi and in Shanghai. So we have a degree, we are a degree granting program. So we have an undergraduate and a PhD program. And last year we moved to a new campus and having very beautiful architecture. So hope you can visit sometime. And also my talk, as you will see, is greatly benefit from the earlier talk. For instance, Pauline's work about like this dynamical system and also the stability. And also we have seen like this feedback mechanism in Yunglong's talk. And also yesterday we have seen about the work about synaptic plasticity. So these pieces will be shown a little bit in my talk. Fine. Oh, okay, yes. So the concept of the dynamical system, the utilizing the dynamical system can even trace back to the Newtonian mechanics. The terminology of the attractor started to be used in 50s and 60s. So this is one of the early definition of the attractors in dynamical system. So let's take a look. So in the study of topological properties of ordinary differential equations, the stability theory of compact invariant sets is considered as a generalization of the critical points, or the limit cycle plays an important role. So by stability of this compact invariant set, we mean that every orbit starting sufficiently close to M will remain in a given neighborhood of M. Okay, so this is called as attractors. So this is all mathematical jargon, but we can extract a few important properties of an attractor. That is the compact invariant set and also the stability. So let's consider the dynamical system, which involves the time evolution of this x state variable, which can be a one dimension or a multi-dimension. Okay? And the dynamic evolution is described by the following equation. Then the state space refers to the all possible x, made of these all possible x. And then compact invariant set means compact is not like infinite, like covering entire space. And then invariant means under this evolution, it will stay within this set. So this is one simplest example of the attractor, the fixed point. So in this fixed point, we can see the fixed points are shown as a color dot here. So not only that, this is like the set itself is not changing over the time. The fixed point is the individual set in this attractor doesn't change in time. That means this f of x is 0. Okay. And then, of course, this attractor is not only limited to the fixed point. It can be a limit cycle or chaotic attractor, which can evolve in time, but they need to stay within this set to be an attractor. Okay? And the second property is a stability, that if the orbit, the trajectory starts nearby, then they need to be attracted toward this attractor. So here in the fixed point example, this region is divided into the basin of the attraction. That is defining the region where it converges to some specific attractor. So based on this property, the invariance and also the stability, the attractor concept start to describe the cognitive processes since the seminal work by Hopfield. So not only the memory system, or some example of the cognitive processes, and one of the application is a memory process. So let's look at the following picture. Do you know? I mean, is there anyone who recognizes this one? Yes, yes. I thought this is a really challenging problem, but yes, you've been to Shanghai, or I gave us some information that I'm from Shanghai. Okay, so from this partial Q, we are able to reconstruct the entire image or the name, right? This is an Oriental Pearl Tower. So this, I mean, the human brain can maintain this information in an associative way, such that with the partial information or noisy cue, we can reconstruct the entire image. So this pattern completion property is benefit from like attractor dynamics. So for instance, this partial cue, noisy cue, or the partial information will set neural state into the one of the Bayesian of the attraction, but not at the attractor exactly. Okay, and then the evolution toward one of the attractor, moving toward the attractor, is corresponding to this pattern completion. So this attractor dynamics is a beneficial for the associative memory. And also we can understand this evolution under the dynamics can under this energy landscape. So here, if there is an energy landscape, then attractor is corresponding to the potential well, the minimum of the potential, such that once you are falling into some region, then the dynamical system tries to minimize this energy and will be attracted to the local minimum, which is corresponding to the attractor. Okay. So not only for the associated memory, the attractor dynamics has been used to describe the decision making. Okay? So we are making a decision, big or small decision every day. So for instance, during the break, you may feel thirsty, and there are available options like a water or the juice. And maybe you need to choose one of them. And according to the attractor theory, like these are corresponding to the attractor. Each decision is corresponding to the attractor, which compete each other. So if you are considering the similar task, which is a perceptual discrimination task, like a perceptual decision-making task, like in this experiment, monkey need to make a decision. They are watching the screen, and on the screen, there are visual random dots, like they are moving like randomly, but there is some coherence in some direction. Okay, so with a noisy input and then some coherence direction, you need to make a decision either left or right. Then this left or right corresponds to the different attractor under these models. Okay, so if you are assuming that there is some leftward coherent motion, okay, then in the state space consisting of these neural activities, there are two attractors corresponding to each decision, left decision or the right decision. And with some coherent movement toward the left one, the Bayesian of the attraction, one of the attractor will be slightly dominant than the other. Okay. However, the initial state will start at the middle, like this potential here. Okay. So this is an undecided state, but with this noisy input, some fluctuation, and then some coherence motion, it will fall into the one of the attractor. Then this system can be still sensitive to the initial input noise. Okay. However, once there is enough information is received, then it can be fall into the one of the attractor rapidly and efficiently. So I think Tianming will introduce the different model of decision making, and compared to the linear model, this nonlinear attractor model is shown to be robust and efficient. Yes? Oh, so this is based on the neural circuit model. So in a neural circuit, so this is kind of a dimensionality reduction already done. So in a population of the neurons, let's consider. And then there are two, you can imagine that there are two populations, subpopulation representing each decision, right? And then they are forming this attractor within each population. And so this is a kind of a average population activity you can consider, like a population activity 1 representing the left decision, population activity for the right decision. Yes. Oh, so what you're asking is, so what I understand is this is the bottom-up model, I have to say. So they are implemented, the connectivity is kind of a tune to generate such an attractor. And then they are having these two attractor in the low-dimensional dynamics, yes. But also there are the technique nowadays try to find out this low-dimensional attractor from the neural data directly, yes. Mm-hmm. Okay, so this is application to the decision making. And then the last example I would like to illustrate is the attractor dynamics for working memory. So working memory refers to our ability to maintain information transiently in our mind without the external input. So let's consider the following example. So we have seen this abstract pattern on the screen or on your phone. And you would like to, this Q is related to the signage of the store you are looking for in this busy Shanghai street, for instance. Then as you move across the street, your gaze shifts from one place to the other, and you will find the right match, and here it is. And then until you find the right match, you need to memorize this stimuli in your mind, right? So maybe this sensory stimuli would not be available to you while you are searching for it. So working memory is critical for many non-trivial computation, okay? Because the sensory stimuli is not always available. So in some tasks, in the working memory task, it has been suggested that memorizing such a different, it's confusing, yes. So memorizing these different abstract stimuli is related to the invariance property of this attractor. So they are corresponding to the different attractor in the state space. And once this pattern is present to you during the stimulus presentation, then it is moved from some attractor which is corresponding to the baseline. And then with the presentation, it will move to the one of the Bayesian of the attraction. And then after the withdrawal of this transient input, due to the invariance property, you will be attracted and will stay there. Okay? So this invariance property and attractor dynamics has been related to the neural correlate of the working memory. So for instance, this is a similar task. Monkey was shown this abstract pattern, and then this appears transiently and followed by this some delay period. And after the delay period, it needs to find the right match to get a reward. And neurons in a inferior temporal cortex has shown persistent elevated activity during the delay period. Okay? So this is one example inferior temporal IT neuron showing the selective activity for a particular stimuli. Okay? So this can convey the information toward the, at the end of the delay period by decoding which neuron fires most. Okay? Yes? Yes, I mean, you can consider that as a Hopfield network, and Hopfield network can serve as this working memory circuit as well. However, like whole-field network also described this synaptic plasticity, what type of connection is required to form the attractor dynamics, right? Yes. Yes. Yes, yes. I mean, so to describe the discrete attractor, the whole-field like network can work. Yes. So, like, based on this attractor property, this concept of the attractor has been used to describe many cognitive processes. And today, I will focus on the different attractor model for the working memory. And then I will choose the mechanistic model. And then in this mechanistic model, I will describe how this attractor is formed, like what is the required network connectivity, and also what type of synaptic plasticity is required. And if time allows, I will talk about the alternative network model at the end. And then this is today's one. And then tomorrow, I will talk about the extension. So today, I will mostly talk about this local circuit model. But tomorrow, I will talk about the extension of this discussion to the modular interaction between the sensory and the memory area. Okay? So here, I show the example of a working memory for the object, right? Some abstract pattern you need to memorize, and then there was this persistent activity you have seen. Only for the object working memory, there are different type of working memory observed. So for instance, in this task, monkey needs to memorize the spatial cue, like a spatial location, during the delay period, and at the end of the delay period, it needs to make a saccade where the cue appears. Okay? And then this is an example neuron in the prefrontal cortex showing the elevated persistent activity, which is also selective to the spatial location. So this neuron shows the elevated persistent activity at the 270 degree. Okay? So in this case, different neuron fires has a different preferred location. So by looking at which neuron fire most, then you can decode the information at the end of the delay period. So this is the tuning curve, memory tuning curve of, for the spatial working memory. So this is a previous example neuron showing so this is average memory activity, and this neuron shows the peak around the 270 degree, its preferred location. But not only this type of working memory, we also have observed the parametric working memory. So like a spatial location is bearing on the ring, while like in this parametric working memory, the stimulus you have to memorize varies monotonically, such as the stimulus frequency. Okay? So in the stimulus frequency, like the monkey needs to memorize, then this neuron shows the monotonic tuning curve. Like for the lower stimulus frequency, the memory activity was lower, and then for the higher stimulus, the memory frequency, the firing rate is higher, or there can be an opposite trend, like a negative tuning as well. Okay, but both shows the monotonic tuning curve, and then this type of working memory is called as amplitude coding. So this is called as a location coding. By looking at which neuron fire most, you can decode the information. On the other hand, in the amplitude coding, you need to look at the rate of the activity, right? If it fires most, then this was a higher frequency, and then lower, then it's a lower frequency. Okay? But these two types of working memory, spatial working memory or parametric working memory, are different from the working memory. Maybe I will, because the stimuli you need to memorize are continuous, right? The previous one is a discrete, like a discrete object, while this varies smoothly on this stimulus space like a location or the stimulus frequency. Yes?
Sorry, just to clarify, what exactly is the stimulus on the right-hand side?
Yes, here, this is the experiment done in a Lomos lab. So in this experiment, monkey receive a vibrotactile stimulus on its fingertip. So this vibrotactile stimulus varies within this range. And after the delay period, another stimuli comes, and then they need to compare which frequency was higher. Okay? So it requires a memory of the original stimulus frequency. Yes. Okay, so what I want to deliver here is there were different type of working memory. And then this is some summary of time scale for the working memory related persistent activity. So working memory related persistent activity has been observed in a wide range of the area, like in vivo or in vitro. But typical time scale for this is on the magnitude of at least 100 milliseconds to the usually on the few seconds. Okay. However, we know that the time scale of individual neuron typically lasts on the time scale of at most the milliseconds or tens of the milliseconds. Okay. So to bridge the gap, we need to think about the network interaction. So in this simplified circuit model, sorry for running long, this is a point neuron again. Yes. So yes, in this one, we have a leaky neuron. That is, this point neuron receive transient input. Then it follows it elicits some firing in this point neuron, but it decays back to the baseline depending on its intrinsic time scale, like 10 to 100 milliseconds at most. However, as I mentioned, the time scale for the persistent activity is on the scale of seconds, few to few tenths of the seconds. And to prolong the memory duration, the network interaction has been suggested. So like as we have seen as a regenerative mechanism, like this network connection, not within a single neuron itself, but if the neuron are connected through the excitatory connection, then the activity can reverberate through this positive feedback loop, and it can prolong the memory duration. Okay? So this is kind of a popular model for the working memory. And to get the further idea, I will give you a really simple introduction to the dynamic system of this rate model. This is a so simple model, but this will give you some good intuition what is required for the network to maintain such a persistent activity. Okay. So in this rate model, let's consider the local population model for the local population of the activity, and the activity is described by this fire rate Ri. Okay, and note that this Ri usually represents not the activity of a single neuron, usually a population of the neuron. Okay, and then Ri is the representative firing of this population. So, and then this Ri, these neurons or the subpopulation are connected through the this synaptic connection, the way it is denoted as a Wij. And so the synaptic input here is a recurrent input, which is a weighted average of this presynaptic fire rates, and there is external input coming in. And there are the different formulation, but in this Wilson-Kwan type of a model, we have a synaptic input summed first, and then it is transferred through this nonlinear transfer function to the current. And then it is a transfer to the rate. So this is called as an input-output transfer function. And then without any external input, it is modeled that this neuron will be like attracted toward the baseline first, and then that time constant, that decay is modeled as this tau I. So this is on the time scale of 10 to 100 milliseconds at most. Okay. So this is a typical rate model we can consider, and then let's consider even simpler case. Just let's consider one population, and then even there is no like nonlinearity here. Okay. Then we have this one. It's not difficult. Just I will write. So we have I missed the tau there. I just realized. So for the one population, I will leave this out because I will consider the linear input-output transfer function, then WR plus I. So if I rewrite this, then I want WR plus I. And here we are just considering the fixed point property. That means when this becomes 0, we will concern, right? And then we assume that external input is a 0 during this period. That means like the important point is when W is equal to 1, right? So if W here is less than 1, this is a negative, right? So this is negative means like this will like tau 1 minus W R dr dt minus R. So it will decay back to the baseline with the new effective time constant here, right? And as this effective time constant W is closer to 1, this time constant would get longer and longer, right? So it will decay more slowly. And then when W is greater than 1, then this system will blow up to the infinity or the negative infinity. And in the middle, W equal to 1, then it gives us this is a bifurcation point, okay? So when this becomes 1, tau dr dt is equal to the external input, right? Because this intrinsic leakage and then recurrent input cancels each other. So there remains only the external input. So dr dt, the R would be just integration of the external input over time, right? So that means if we had the external input transiently, then this has an integrator property. So this transient input can be integrated during this period. And since this is an integrator, for the different strengths of the input, it will more rapidly increase during this period. And after the withdrawal, it can maintain its activity at a different level. So with this integrator property, actually this might be a good model for the amplitude coding I mentioned about previously, right? So here we can see the requirement to have an amplitude coding for the this line attractor working memory. That is, like we need a sufficient excitatory feedback, right? W needs to be strong enough to cancel the intrinsic leakage, and it requires a fine tuning, right? So the line attractor, it requires a positive feedback, but some kinds of tuning condition. If it is mistuned, if it is not exactly 1, then effective time constant will be proportional to this, inversely proportional to this deviation, right? If it is 10 milliseconds, for instance, and then the deviation was like a 1%, like a 0.01, like then this is a 0.01, then time constant will be like 1 second in this case, right? If it is a 0.1, further deviated, then that would be like 100 milliseconds. So further and further deviation will make the efficient time constant smaller and smaller, right? So, okay. Any questions so far? This is a simple math, right? Okay. So this is a case for the line attractor. Oh, yes. It's fine, yes.
For excitatory network and inhibitory, it looks like the parameters
Ah.
for W, is that supposed to be greater than 1 for inhibitory? Or
I mean, here, I mean, this is a simple circuit, and then I didn't mention very much. But if it is excitatory, that means overall W is positive, right? Still, there is some of the amplification because this denominator is less than 1, okay? And then this time constant is effectively small. So the typical excitatory network, if it is only composed of the excitatory network, what you can expect is there will be amplification due to this passive feedback, reverberation, but the time scale gets slower. I mean, this is a generally good kinds of intuition you can have from the simple model. If it is a excitatory network, like, yeah, this is a less than 0, so this is a typo, sorry. Yes, then like a denominator is a greater than 1, so attenuation of the input together with the faster response, okay? Yes. Thank you. So this is like the case where W equal to 1 and can have infinitely many, like the attractors in this case. On the other hand, this doesn't respond. Yes. However, like this, like a linear input-output nonlinearity is not typical case. Like I will get back to this point, like how, I mean, make the approximately the system to maintain this linear like relationship. But typically, we have a nonlinear input-output transfer function, right? For instance, like because fire rate cannot be negative, so there should be a threshold nonlinearity that, like when the input is small, the fire rate wouldn't be 0, wouldn't be negative still, right? With the threshold nonlinearity. Or we also prevent the like a saturation nonlinearity, like the fire rate cannot be infinitely large, right? So for instance, here, if we are considering the phi, which is the sigmoidal nonlinearity, right? Which has both like this threshold nonlinearity and also like this saturation nonlinearity, then if we don't have any external input yet, then in the state space analysis, trying to find the attractor or the fixed point, this is just like a drdt is a minus r. So this one-dimensional state analysis typically draw the r versus drdt, okay? And r versus drdt is just a straight line and has this fixed point at the 0, which is corresponding to the baseline. Okay? So baseline is stable. But if we have a stronger and a stronger recurrent input like a W here, shown as a J here, J gets stronger and stronger. The system gets enough positive feedback. And in the state space, the null line is changing, increasing. And then this sigmoidal shape increases faster. And then it can have a two attractor. Like the 0 is the first critical points. But here, there is the slope needs to change from positive to the negative sign to be an attractor, so that below it there is like increasing, and above it needs to decrease. So this is one attractor, but there emerges another attractor, which is now elevated persistent activity, maybe for the one object. Okay, so you can see that here again the requirement is similar. Like it requires the strong positive feedback, right? And then you can notice that as you change this strength, J or the W, the system, when this J is sufficiently large, in this case like larger than 16, then it can make another attractor, right? But even if there is some variability, like J equal 20 or J equal 30, still there is an attractor, one attractor. So unlike the previous line attractor model, which requires a fine tuning, right? This discrete attractor model, like forming one attractor, requires a less fine tuning condition. It's utilizing the strong positive feedback and then nonlinearity. Okay? Yes? Can you say that again? Sorry. Ah. So this is a neuronal model we are considering mostly. So we are trying to adapt the neuronal input-output transfer function. So in the mathematical side, the typical choice could have been like this sigmoid nonlinearity, which has both threshold nonlinearity and then saturation nonlinearity. Or some cases, the people prefer to use only like a rectified linear function, which only has this threshold nonlinearity, but it features well for the low fire rate or the reasonable fire rate range. And then like recently, the people tried to use the supra-nonlinear function, like which is increasing quadratically or more than, the higher power. And that is kind of inspired by the BI relationship that people have observed. Like, so in the visual cortex, they measure like this relationship between when they give the input, how the voltage changes. And then they have found this quadratic nonlinearity. And so there are the various choices, which is inspired by electrophysiology. Also, like there have been many different choices in the math side. Yes, but it's mostly inspired by a neuronal nonlinearity. Yes. Okay. Yes. Oh, here J is equal to W. Yes. Okay. I found many typo. No. I forgot which is my order. Okay, so far so good. All right. So with this intuition in mind, let's now discuss like what is required. How we can build a discrete attractor model. So the previous example, like one population with a sufficiently strong positive feedback and then nonlinearity, we can generate one attractor. There were two attractors, basically, one for the baseline and then one for the elevated persistent activity. If you want to have a multiple attractor to represent the multiple stimuli, for instance, right, we can use this idea and having the multiple population, subpopulation, such that individual populations are strongly connected to each other so that it can generate the strong positive feedback, right? And then like this can store the P item, for instance, so there will be a strong positive feedback with a nonlinearity, but also to have some coordination of this pattern across the different attractor, like when one is active, then you don't want to activate the other remaining population, right? So this can be achieved by having the global inhibition here. Okay? So utilizing local excitation and a global inhibition, you can generate the persistent activity, which is selective to the specific pattern. So this is the simulation of the network activity for discrete memory. So like this one is the active population. So after the offset of the this input, it can maintain the elevated activity, while E cells selective to the other stimuli doesn't maintain this elevated activity. Yes? Stronger connectivity, stronger positive feedback. Yes, so within the population, remember that to maintain the information, right, the reverberation, you require the strong positive feedback, right? So we want to have so you want to have this elevated persistent activity for population 1, for instance, right? Then you require the stronger connectivity within these neurons. Yes, yes? So in this model, like originally they didn't have a selectivity, but there can be a special selectivity. If you consider that, like there is a E cells, right? Like I will show soon about this special pattern which has shown, which was shown in the Pauline's work. But like inhibitory neuron, for instance, like is a there are two ways you can make a global inhibition, right? So one way is like there are only one population receiving all input and then fed back. Like then this neuron represents just a persistent activity no matter which one is active, right? On the other hand, you can have a I1, I2, I3, which can be selective to the E1, E2, E3, and then this is connected to each other. Then you can develop the spatial selectivity in the inhibitory neurons, right? On the other hand, if the projection is wider, right, then still it can generate the spatially selective, the global inhibition in this case. Yes. So in this case, we want to have a E to E connection more selective, and the E to I to E, which I didn't show here, but this is a kind of an inhibitory feedback loop, and the inhibitory feedback loop would be wider, so that like it will inhibits the other population. Okay, but later I will show you that also there are different type of working memory, which is called, which is based on the balance of the excitation and the inhibition. In such a model, like rather than this kinds of wider inhibition, actually inhibitory one, the tuning is narrower. Okay, so there are different type of memory, but for this discrete working memory type, usually local excitation and a global inhibition was kind of a key idea. Yes. Okay. So this is a discrete attractor model. Sorry. And then, but I mentioned about the different type of attractor model, like not only like memorizing the discrete item, and which requires a less fine-tuning condition. There are continuous attractor model like parametric working memory and a spatial working memory. And I mentioned, okay, yeah, I mentioned that at least like a line attractor model, like the linear case, and then finely tuned positive feedback model, it can create this line attractor. And then like attractor like model, like for the spatial working memory, we can construct this spatial working memory as similarly to this like a discrete object, discrete working memory. So in this case, let's consider that neurons is representing like it's a different preferred feature, like a different orientation or the location. And then still local excitation, the stronger connectivity between the neurons with a similar feature is required for the positive feedback so that it can maintain its activity. But to prevent the like explosion or like all patterns, like all neurons are active together, it requires the lateral inhibition. Okay. And this one is like as mentioned in Pauline's work, it was like it can be shown how this type of bump-like activity can emerge by analyzing the stability of this, like the baseline activity through the Turing bifurcation. However, one note is that like to form this continuous attractor compared to this discrete attractor model, in the discrete attractor, there is some leverage. You can have a slightly larger or the smaller the weight, the positive feedback. Still, with the nonlinearity, this discrete attractor can be maintained. However, in the spatially extended model or for the spatial working memory, all memory, like all stimuli, needs to be well represented, right? Then it requires a fine-tuning condition such that like this W, so W is now connectivity between the neurons with the preferred feature zeta prime and the zeta. And this set W is a translation invariant, that is, regardless of its center, it has exactly the same form. And then like this Mexican head type of local excitation and global inhibition, lateral inhibition is required. Okay. So this is ensuring some of the translation invariant property so that every stimuli will be well represented and then maintained. And then this is a bump attractor model which can, based on this local excitation and then global inhibition, after this neuron receive some input around the 180, this network, then this can be maintained in this bump-like activity during the delay period. And as I mentioned, although this is a local excitation and global inhibition model, still inhibitory neuron shows some selectivity because it has some selectivity from the E to I connection, but I to E connection can be wider and then it can generate a lateral inhibition in this model. Okay, so then this is the implementation of the line attractor model. I already have shown how to generate the line attractor through the positive feedback, finely tune the positive feedback, right? So in this case, I particularly assume that in our previous case for the discrete attractor, special working memory, I assume that nonlinearity exists, right? On the other hand, I, on purpose, assume that there is no nonlinearity, and then when the W positive is exactly canceling the intrinsic leakage, then the network can be an integrator and can maintain the information at any level. However, this is not realistic. So the previous network model tried to implement such a positive feedback by tuning this positive feedback or the connectivity by balancing the saturation and the recruitment. So in this case, you can consider that this different curve is corresponding to the different neuron with a different initial, starting point, like a different bias input. Then when some neuron is rising and saturating, then to make it like a linear line, then you can consider the second one and then add it up and then add it up. So when you add these neurons with a different saturation level and then like a threshold, then you can approximately make it like linear. Okay, so in this circuit, still you can generate the line attractor like behavior. Yes. This one. So this one is like this. So there is a little bit different. So this is derived from the conductance-based model. And in the conductance-based model, like why I'm saying this is that, so previously I said like, so you don't have to switch, maybe. Yes. So I said that the input is like a weighted first, and then the input current is transferred to the this nonlinear function. But there is another way, like in the neural field model, what you have seen is like individual neuronal firing rate is transferred, and then this is added up by its weight. Okay, so here, I think this is a synaptic currents model, like added. Yes. So here, I think this is a contribution from the presynaptic side. Okay, the F within F is a presynaptic side, and then this is a WIJ. You can consider. Yes. So this is a different model, but the basic idea is the same. To cancel out the leakage exactly, you need to tune the positive feedback precisely, and then utilizing this threshold, and then like saturation nonlinearity well. Yes. So this is like the input is approximately the same as the intrinsic leakage, and that at every E points, like every amplitude level, you can maintain the persistent activity. So actually, this is a model for the oculomotor system. So oculomotor system is like when you receive the this velocity signal, then it integrates and then like update the eye position, and without this velocity signal, like the eye gaze is still. So and then this eye gaze, so this E is a different eye level. The eye position, and then it can maintain this persistent activity at any level. Yes. Okay. So the main message you can have here is like there is a positive feedback required. And then for the line attractor or special working memory, we require like some fine-tuning condition in the connectivity, right? Then let's talk about some property of this attractor network. Yes? So like if we are having a one neuron only, right? So in the case, in this example, and then like let's say the simpler case, let's say this is just a 1, slope is a 1 and 0, right? So then in this case, as R increases, then this is the pi WR, for instance, right? Then you have overlap with the R exactly on this period, right? However, in this region, so like when it becomes saturating, like this region, then above this region, minus R will be dominating. So in some region within this area, minus R, and then like this function will be exactly 0, right? So they are canceling each other. That means it can maintain the activity at this level. However, when this is above the certain level, like our threshold or the saturation, then this becomes minus R. R will be dominant than this part. That means DRDT is a negative, right? So it cannot maintain the activity. So with this nonlinearity, it can limit the range where it can maintain the activity. So we are utilizing, so once there is such a neuron, then let's assume that there is another neuron which is start to activate at the different threshold, right? Then now we are utilizing this neuron to extend this region and then like extend this region, for instance. Okay? So this is especially for the line attractor model. You want to maintain the persistent activity at the like different level. Exactly. However, in the discrete attractor model is once it is stimulated, then it will be attracted to the one of the state, right? And then this case doesn't require the fine tuning of the W or like this nonlinearity. Yes. We can talk more. Yes. Okay. So let's discuss some characteristic of a discrete attractor model, like how we can kind of relate it to some behavior of this circuit. So since in this discrete attractor model, the attractors are separated by different basin of the attraction. So it has usually the finite capacity. So it has a limited capacity. But since they are separated with this basin of the attraction, even there is some noise or the perturbation, once you got trapped there, then it is difficult to escape, right? So it's like once you like have record something, I mean like the per or the per tower I have shown. But if you have memorized the different item, maybe you remember the different place, then it is a little bit difficult to get away from this attractor state in the discrete attractor model. Then if you are considering this behavior, like, so here, so this is one of the attractor we are showing, And then there is a repeller, which is corresponding to the heel of this energy. Okay. Then due to this behavior, if you have, so I mentioned about the pattern completion property. Okay. So let's assume that we have a cat attractor and a dog attractor. And then if you are giving the input like with some morphing degree, like from the cat to dog, then the final reports would create like attracting toward one of these potential well, like attractor is creating bias pattern in this attractor model. Okay, so the bias pattern means the initial stimulus can be different from the final state, right? So the bias is the deviation from the set ahead, like which is decoded from the circuit, how much is deviated from the original stimuli. And here, if you start from here, then it will fall into this attractor. That means this amount will be a bias, right? So this discrete attractor model creates the bias toward this attractor, like a positive bias and a negative bias. And then repeller, at the repeller, there is a negative bias and a positive bias above it. And not only in the bias pattern, in the variability, you can also identify whether it comes from a discrete attractor versus a continuous attractor. Because like if there is a constant noise in this system, then this drift force will catch the variability at the attractor. Okay? So even with this constant noise given in this system, then the variability of the variance at the reported one is a minimum at the attractor, while the repeller is amplifying this noise, so it will be maximum. Okay, so there is some distinct characteristic of a bias and a variance pattern in the discrete attractor model. Okay, yes. Oh, yes. Here I adapted from my paper. So what I'm saying is, like, as the time evolves, like, I mean, if you are thinking that this is a very slowly varying, right? You start from here, and then, like, you move to the next point, and then, like, a later period and a later period further and further. So from the initial point to the later point, like, a decoded value will be further away, I mean, in time, right? If we are assuming that this is a slow drift. On the other hand, continuous attractor model is marginally stable along this ring. Like we are thinking that for the spatial information, there will be a ring-like attractor such that it would be like each stimulus on the ring, I mean on the stimulus space is well represented by the ring on this ring on the neural space as well. Then compared to the discrete attractor, this has infinite capacity if we don't have a noise. Okay, number of the items you can memorize, like orientation stimulus is a continuous, but this has some compensation. I mean the trade-off that like it is less robust than the discrete attractor. Discrete attractor is even with some small perturbation, you will get back to the original state, while like in this ring attractor, continuous ring attractor, if the noise is perturbing you, and then you will be relocated to the new location, but the energy landscape is flat, so you will be updated to the new state, right? So with the noise or due to the perturbation, you can stay there. So in the energy landscape, it is flat. So in the bias, I was talking about the trial to trial variability, but in the mean behavior, there will be no bias, like everything is just equal. It will stay in the mean, like under this symmetric fluctuation. On the other hand, noise can accumulate, like with like a left to the right, and then this variability would get larger and larger over the time. So the standard deviation would increase in time. Yes? Yes, here I consider the drift diffusion model. So this is just all one-dimensional, and then the phenomenology, like although we are considering the circuit model, the behavior can be captured in the low-dimensional dynamics, and this low-dimensional dynamics can be described with dx dt is like a minus round u round x. So this is a drift determined by this energy landscape, and then there will be a sigma dB, dW, or dB. Yes. So there will be a constant noise diffusion term we are considering. Okay. Then we are starting from some initial state x0, like this is a stimulus, let's assume. And then we are considering the final state, which is a decoded value, right? Then the mean of this will be the bias. And then in this discrete attractor model, like there is only a few attractors, right? So if you are deviated from the attractor, it will be like attracted to the few like a stable fixed point. So there will be a bias arising. On the other hand, for this continuous attractor model, like x0 and then the final x can be exactly the same on the mean, right? Trial, it can vary, right? However, on mean, in the mean, it can be just 0. Yes. Is it? Yeah. Oh, I mean that this is a Brownian motion, and then so this is a random noise, white noise I'm giving every time. Yeah. So this is a dVdt term. So this is a drift diffusion model I'm describing. Yes. So every time, so this is a deterministic part, like you are considering the mean, then that will be determined by this drift term. On the other hand, the addition of the noise gives the trial-to-trial fluctuation. Like every time step, you are giving the white Gaussian input, yes, additionally, to replicate some behavior fluctuation. Yes? Yes, U is energy. So the system tries to minimize the energy, its negative derivative. Yes. So have this in mind. We can discuss shortly about the experimental evidence for attractor circuit. So the people try to identify whether such an attractor exists in the brain, and they utilize the property of these different attractors. So in Karl Svoboda's lab here, like they consider like the task where mice listen to the music. I mean, there's some different tone in the beginning, and then it followed by some delay period. And then after this delay period, depending on the original sound, it needs to make a leak to the left or to the right. Okay, it sounds like some kinds of a delayed decision-making task, right? And then they were asking whether it is like the information is maintained through the discrete attractor-like dynamics or continuous attractor-like dynamics. So if it is a continuous attractor, then the property of the continuous attractor is it is not robust against the perturbation or noise, right? So, or if it is a discrete attractor model, like corresponding to the left or right decision, leak in the end, then even if there is a sum of the perturbation, it can recover under the perturbation and can make a correct choice, right? However, in the perturbation is large enough, then it can still jump to the new location, and there can be an error trial. This one is a kind of a different initial points. You can maybe initial mental state you can imagine, like yes, or it can you can consider that like I don't know what they have thought like for this variability, but if the continuous the different tone is setting the different level, or like in this discrete attractor model, like it will start at the baseline, but depending on the Q, it can start from the 1 or 0, but this variability, I don't know what they have considered exactly. Yes. So what they have found is this system, this trajectory, which is relevant to this maintenance of the Q information, was kind of a robust against the perturbation. So with the optogenetic stimuli in the middle, there was a perturbation, but it seems like a recovering after the withdrawal of this optogenetic stimuli, while in some trial, there is incorrect trials and can make a wrong decision still. Okay? So this is more consistent with discrete attractor-like dynamics rather than this continuous attractor one. Yes? I don't know. I mean, the details here. I was looking at, but I cannot see that much rebound here clearly, right? What you are saying is after the withdrawal, there should be some kinds of a rebound, right? I mean, what they have considered this as a kind of a tracking back, like there is some perturbation. They are kind of returning back to the original, like a discrete attractor rather than a rebound effect. Yes.
It also depends on which population of neuron they're actually inhibiting, right? This is like, I'm not sure, is it selective inhibition of a population of neuron they're recording, or just a mass inhibition?
I think this is a selective inhibition in the ALM in this area, yes. So this is an example of some of the evidence of the discrete attractor. On the other hand, continuous attractor is like it can be like there can be some drift of the bump activity. And then the drift of the bump activity, of course, the mean is a zero, like it can move to the left or it can move to the right. On average, the bias will be zero, but trial to trial, this fluctuation can result in some error in the behavior as well. So in a COMTEST group, what they have measured was like in this special working memory task, the monkey needs to make a saccade, right? But this final saccade location is not exact. So there can be some of the deviation, like counterclockwise, like a deviation or a clockwise deviation. And then like they have found this deviation in the behavior, and then measure the deviation of the tuning curve. They could obtain this tuning curve of during the memory activity and how the center changes over the delay period, right? And what they have found is this tuning is the tuning deviation from the left or to the right clockwise or the counterclockwise is quite correlated with this behavior, like error in the behavior as well. Yes? Yes. Yes. Yes, yes. I think, so here what I think, is that the stimuli, the attractor geometry follows the geometry of the stimuli, right? So like when you have a left versus right decision, right, left, then I don't know the reason why we need to think about the continuous attractor model, right? It requires additional, like in the memory stage, you can make a continuous attractor, and then in the end, you need to make a decision. That means you need still some kinds of a binary choice, right? So and then this is a continuous one, like a stimuli is a continuous, so it is well represented by a continuous attractor, not by a context, but I will talk about next time that some evidence suggesting even for the orientation stimuli, it may utilize some feature of the discrete attractor. Yes, okay, but I will talk about it later. Yes. So this is the experiment evidence I mentioned about. And then, so the formation of this attractor model, like in a classical Hopfield-like one, like as it is pointed out, the Hopfield-like network can create this discrete attractor. And then like a Hebbian learning was suggested. Like if we said that, I said that like the two neurons having a similar preferred feature requires a stronger positive feedback, right? And this stronger positive feedback can be created through the Hebbian-like learning rule, such that if two neurons are repeatedly excited with a similar stimulus, then the connection between them gets stronger. However, for the continuous attractor model, it requires additional condition. Maybe in the formation, it utilizes this heavier learning. However, the maintenance, this like the translation invariance property requires the different forms such as homeostatic plasticity. So for instance, in this work, like to maintain the ring-like attractor model, like homeostatic plasticity, that is like regularizing the fire rate, the average fire rate of postsynaptic neuron. Like here, the delta Wij is a form of the synaptic plasticity. This is updated depending on the activity of, in this case, only the postsynaptic neuron and the weight. And this R0 you can consider is a kind of a long-term average of this rate. And then you want to make this a long-term average to be kind of a constant. So to have some kinds of symmetry in the system, you need a regularization. So in this specific case, in the traditional link-like network, they perturb the property of the individual neuron. Okay, so far we only consider some kinds of a homogeneous case, like all neuron has this translation invariant connectivity, and then like input-output transfer function is all the same. But if you are kind of mistuned this, like having a heterogeneity in the postsynaptic input-output transfer function, then it can easily form a discrete attractor. So that is kind of a perturbation in the connectivity. And then you can, from the continuous attractor, you can easily form the discrete attractor. However, by having this homeostatic plasticity, you regularize the connectivity, and then you could recover this special ring-like attractor. Yes, this is a homeostatic one, and then like yes, in this particular case, yes. 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 I mean, with this, so this is a kind of a special case that if you have some postsynaptic perturbation, okay, and then like this is kind of as Lava mentioned, this is a postsynaptic regularization again, right? So with this combination, there was some postsynaptic perturbation, and then regularizing the postsynaptic fire rate average through this form of the homeostatic plasticity, then you could recover this continuous attractor. Yes. On the other hand, I mentioned that this is only for the particular perturbation. If you have not this postsynaptic one, like in the output synapses, if there is some heterogeneity, or even line attractor model, this homeostatic plasticity didn't work well. So instead, if you are regularizing the this is a kind of a Hebbian type. It's activity dependent, but this is called as a differential plasticity because it is proportional to the negative derivative of a postsynaptic activity. Yes? Here, I don't have a Hebbian type of plasticity. What it started is they started with a ring attractor, traditional ring attractor model, which is perfectly tuned. And then they perturb the function of the individual neuron. Okay, so there is you can consider that it's like a postsynaptic perturbation. Individual neuron has this perturbation, and then it easily forms this discrete attractor in such a case. Okay. On the other hand, when you put So under this perturbation, when you put this type of homeostatic plasticity, like if it is below 0, then you are potentiating this connectivity. While if it is above R0, then you are like decreasing the connectivity. So with this type of homeostatic plasticity, you could regularize like all activity representation, and then it could restore this ring attractor dynamics. Yes, exactly. Yes, yes, yes. So this is the same for like a differential plasticity. If you are regularizing the derivative of the postsynaptic activity, it is somewhat expected. If there is a drift of the activity, then you are detecting it. And then penalizing it. If it is a positive drift, then you are decreasing the activity. Or if it is decreasing, then you are increasing the connectivity, right? So this differential plasticity was known to recover this not the ring-like, the line attractor-like property. Okay, so with the differential plasticity is known for the line attractor, and then what they have found was combination of this differential and homeostatic plasticity could recover like this like a ring-like the special working memory for the various type of perturbation. So there is some compensation of the differential and homeostatic plasticity together, working together. Okay? Yes? So what I mentioned is the homeostatic plasticity worked well for only the postsynaptic and the global one, but it couldn't recover these kinds of ring-like architecture for the presynaptic one, for instance. However, when you combine the differential and the homeostatic plasticity together, then it could recover the ring-like the ring attractor model well across many different types of perturbation. Yes. So there is a compensation between these two. Yes. Yes. Exactly. Yes. Yes. The network can easily form a discrete attractor. I mean, I have to say, like because of this excess of the positive feedback in some place, and then I mean, still the positive feedback is strong. Like, however, little bit of more excess of the positive feedback here, and then a little bit like W is greater than 1 here, and W is less than 1, even if they are close to 1, right? Then easily like the attractor is formed to the place where W is greater than 1. Yes. Uh, Actually, this might be related to this. I don't know. Yes, I mean the number of this attractor is determined by where I mean that this excess and then deficit of positive feedback occurs. I mean and then I don't know exactly it's related to the frequency of a noise, but we can discuss more. But in this case, what I think might be connected is like I talked about like a few discrete attractor previously, which is a detrimentor. I mean for the continuous attractor model, right? Like because like you are starting from 30 degree, and then you are attracted to the 0, then that would be a too much loss of the information, right? However, like this continuous attractor model has some kinds of a problem because it is so sensitive to the noise. So the people try to remedy this problem in a various way. Like one is like approximating this continuous attractor with many discrete attractor. Okay, and then like this can endow some kinds of robustness against the noise. I don't know whether it can answer your question. But also, like, there is a mitigation through the short-term synaptic plasticity. I only talk about like this connectivity, tuning of the connectivity so far. However, the people also consider the short-term plasticity for the working memory model, like the short-term plasticity, like a short-term facilitation or short-term depression. Mostly for the working memory, people have considered the short-term facilitation such that the connectivity between the neuron is not fixed, but is transiently increasing depending on the activity, presynaptic activity. Okay. With this facilitation, which typically has a long time scale compared to the intrinsic neuronal or synaptic time scale, if you are making the intrinsic time scale longer with this facilitation, then it also has some regularization effect and then make the continuous attractor stronger. And also, in our lab, not my lab, when I was a postdoc at the Goldman, with the Mark Goldman, we consider that like the positive feedback is too sensitive. I mean, too many type of perturbation. Okay, so here we consider the different type of synaptic connectivity, which is called as a negative derivative feedback. This is similar to the plasticity model I mentioned previously. So, but this derivative is penalized through the synaptic dynamics. So let's consider that, like there is a memory cell, like a one cell we have discussed, or one population, and then there is a sleep detector mechanism, such that if there is a slippage in this persistent activity, negative derivative or positive derivative, then this is giving the negative derivative, so the corrective force, okay? Then it can maintain the persistent activity. So this is a bit different from the traditional positive feedback, like the network connectivity feedback is generating the derivative-like input. And this derivative-like input is actually somewhat consistent with neurophysiology in a prefrontal area. So like the negative derivative feedback can arise from the balanced excitation, positive feedback, and then negative feedback. But typically the people, when they consider the excitation and the inhibition, the people consider the excitation is a little bit slower compared to the inhibition. Inhibition is faster. On the other hand, like there is an NMDA synapses in the this prefrontal area, and then E to E connection in the prefrontal area is known to be slightly longer than an E to I connection. Then this can create a slower positive feedback. Then with a delay in the positive feedback, which is shown as a blue curve here. So if there is a change in the activity, then inhibition in this case is faster compared to the positive feedback. And due to this time difference, synaptic time difference, it can create like an input transiently and give a corrective signal. So this is kind of consistent with the balanced ENI, which is observed in many cortical area. And then this can create the irregular spiking activity we have seen previously. And more importantly, this network was shown to be robust against many different types of perturbation, because loss of the some cells or change in the intrinsic gain or all excitatory synapses or all inhibitory synapses, some kinds of a modulation which is prevalent in the circuit. Under this condition, the positive feedback can deviate from this perfect tuning easily and create this kinds of decay or like a blow up of the activity easily, while in the derivative feedback, like the cancellation occurs like a balanced condition is like either some loss of the cells is decreasing the positive feedback but decreasing the negative feedback together. So it can still create this persistent activity well. And we have shown that this derivative feedback mechanism can occur for both line attractor model or special working memory type. Okay. So I think I exceed the time, so maybe I don't have time for discussing the alternative network mechanism. But I can discuss more after like a break. Yes. Okay. So if there is any question in the material so far, please let me know. Okay.
For example, when we model, I don't know, any function of the brain with attractors and like as a nonlinear dynamical system, I understand it. But when it comes to the whole, like modeling of the whole brain activity, can it be modeled like that? Should you add like a lot of models of various functions together, like put a lot of attractors together? How should it work in this sense?
I don't know whether I can connect it to the police work. Police work was more about this global activity, but he showed that this is more dynamic and then transient. And then what we have, what I will discuss tomorrow actually is that like Attractor is a beneficial for the maintenance and stability, right? However, like we found that there requires some kinds of, like for instance, for the sensory system, right? For the sensory system, it would be good to have some not strong recurrent connection. I mean, maybe it is like a strong recurrent connection, balanced excitation and inhibition, but maybe more dominant inhibitory region, such that it would not maintain the persistent activity there by itself. But there is some benefit of having not strong, like not having an attractor in this visual system. And then when we connect this visual system together with the attractor, there emerges some, it can fulfill the other function together. So at this point, so the people say that whether it would be good to have some visual working memory, for instance, like, so having a working memory dynamics within the visual system as well. However, and then like the prefrontal cortex, having like an attractor for the different type of memory, like more like abstract rules, and then like a more detailed information in the visual area. However, I believe that like a sensory area with a more transient input and then like a faster tracking ability, it has its own benefit. Yes.
All right, and another question about the attractors. Like if we, for example, talk about about sensory systems, as we know they are being progressed as same as we are getting older, right? So we are born with something, but we learn understanding the visual information according to our childhood. So how do like attractor, change its properties, or how it works during the like development of our brain, of our sensory systems?
The developmental study of the attractor very much, but at least what I want to add is that like the special working memory I was talking about, I feel like the attractor is kind of a reasonable, like, so the part I didn't show here is like the second part was, this last part is about like why the persistent activity is needed or like attractor is needed. So here in this work, like in the RNN, the people try to see where the attractor like or persistent activity emerges, in the training. And what people have said is like in this study, they put the activity silent, the synaptic short-term plasticity together with this connectivity. And then when they train, like in the working memory task, like requiring more manipulation of the information, then they said that attractor-like dynamics is more beneficial rather than like a synaptic memory, for instance. So like spatial working memory, for instance, I feel like we are utilizing this spatial information constantly, right? That means we need to manipulate and then access this information constantly. Then having a stable representation is helpful, right? On the other hand, like what they have, the shown was not included in this work, but we have this delayed decision-making tasks trained. And then, like, depending on the task output, everything is exactly the same, but task output was slightly different. Then, depending on the task output, sometimes it develops attractor-like dynamics, and sometimes it generates the rotation-like dynamics. So in the rule, like, the system, like, not the spatial information orientation stimuli we need to encode, but which is learnable and trainable, maybe it can develop the different, like sometimes attractor and sometimes the rotation-like dynamics. Yes.
Thank you very much.
Sure.
So for a long time, these continuous attractor were purely construct. Beautiful example in head direction cell in the fly. Also, remember that there is some work in of Vivek Jariman to show why this is not discrete. Is it one of your scenario or?
Why it should be a continuous? I remember they showed that the continuous attractor so I mean the structure exists, but I cannot recall why question there. Yes, yeah.
So I think they have studied it a bit why it's continuous.
I
actually.
see. Okay.